Hello, my name is Charlie Kepler. I'm an applications engineer and lead pilot here at Headwall Photonics, and today I'm going to walk you through the steps for taking your raw data after a hyperspectral mission and converting it to reflectance, along with generating your post-process SBET, SBET GPS file, and processing your LiDAR data to a digital elevation model if you have one. And this system does have LiDAR, so we're now going to go and do our LiDAR processing. So I'm going to open up LiDAR tools, and I'm going to navigate to my data set. And choose this LiDAR PCAP IDX file. By default, it's going to generate this lidar.las file, and you have two options here. Either you can choose the from and to times, or you can say match HS data. So if you're going to choose the from and to times, you want to exclude the times when we were on the ground, when we were raising to altitude, and things like that. And so you can choose that by running the HPI trajectory plotter. I'm going to run this file. It's going to ask me to choose the imugps.txt file from this flight. Select imugps data. And then open. So first we have this figure 5. That's what we're going to look at. This shows the whole flight, which it looks like we have 1, 2, 3 sections where we were doing a north-south pattern, and then 1, 2 sections where we're doing an east-west pattern. And this is what the full flight looked like. It was a big double grid. We see altitude, latitude, longitude, and speed versus time, roll, pitch, and yaw versus time, and then an image of the trajectory versus the polygon. And so we can see when we were inside the polygon, we were collecting. When we were outside, we were mostly turning or taxiing back to our takeoff location. So the figure that we want to look at is figure 5. And so if we were going to select a specific start to and from time, you could click on the map and say, okay, well, I only want to look at, we'll say this section between here and here. And so I want to go between 7:33 and 11:99, so on and so forth. But for today, instead, we will choose the match HS data. And instead of doing a from and to time, it'll only generate a LiDAR file for each time that there's hyperspectral data as well. So the first thing that I notice is my roll, pitch, and yaw are 90, 0, 0, which is the default values, not the values that Headwall has come up with for this system. So I'm going to close out of this, and I'm going to go back into the data set, and it looks like I do not have a LiDAR INI file in this folder. So I'm going to look, and I think I may already have one in my process folder, so I'm going to copy that and put that here. So now when I open that LiDAR tools program again, it'll find this INI file and it'll find the correct values instead of the default values. Your LiDAR INI file should be in your C Headwall sensor config folder. C Headwall sensor config, and then this is the VNear, which is NHP 900, and you can find your LiDAR INI file within that folder. If I launch it again, we'll choose that input file. and it found that correct roll, pitch, yaw entries. And so we have match HS data, so it's only going to generate LiDAR data when there's also hyperspectral data, so it'll ignore the turns and anything before and after. And so we'll keep that. We want use post-process file checked along with save timestamps. We don't want use pps.text checked unless this is a legacy system. And so now that we are good with that, we can say go. And this is going to create a LAS file that is the same time as the frame index file. So each hyperspectral file will have a associated LAS file that goes along with it. Okay, now it says finished and hit 100%. And so we can minimize that. And now we're going to open up Cloud Compare, which is a free software you can download. And it is for visualizing and viewing the point clouds. So I'm going to say File, Open, and I'm going to find those last files we just generated. And I'm going to select all of them. Apply all, yes to all. It's going to load them all in one by one. Okay, so they have all loaded in. I'm going to select each file. If you do the from to 2 times, you'll just have one file instead of all of them. But in this case, we're going to select each of them, and then we're going to do merge. Do you want to generate a scalar field with the original cloud index? Yes. And now we have just one here. So I'm going to go to Tools, Projection, Export Coordinates to Scalar Field in the Z direction. And now we have all of our files combined into one, and they are all colored based on altitude. So if we change this here, we can make the tops of the trees red and the ground blue. And now that kind of looks like what we're expecting. Here's a parking lot, here's a pond, here's a building, here's the corner of our building, and another parking lot and a bunch of trees scattered throughout. So what I do next is I'm going to look at it from the side. You can also hit one of these buttons to reorient. And the first thing I notice is there's some points scattered in the sky. And so if I change my point value to a bigger number, 7 or something, now we can see there's some extraneous points in the sky. You'll find you'll get more of these on a bright sunny day as the sun has, we get reflections from the sun. And then when we see them in the sky, we also see some underground as well. And these are obviously not real. So you have two options. You can click the statistical outlier removal, and it'll go through and it'll remove points that it thinks are outliers. This takes a little bit longer time and can actually get rid of some good points. So instead, we typically will do this snipping tool, segment tool, and I'm going to click and get rid of all the points that I don't want. And when I'm done, I right click. And now everything that's within this bounding area is essentially going to be punched through and taken out. So if I click segment out, and then check. And now you can see now I have two. I have the ones that I got rid of and then the remaining. And if let's turn off the ones I got rid of. And if I look around now, you can see, are there any ones that I still want to remove? So maybe if it looks like there's one right there potentially. So maybe I'll do this process one more time. I'm not sure what that one is, so I'll just take that one out because I don't think I need that. And looks like there's maybe one right over here that's kind of an outlier as well. I'll take out those two guys, and I think then that's good enough. Maybe that guy too. Okay, and what I'm looking for is, I don't necessarily care too much if they're outside of my collection area, but since I did match HS data, this whole area is my collection area. And so I want to make sure that everything makes sense because I don't want to have points that are throwing off my calculation. For example, if I'm using a max or a min DEM, I don't want that to be the point that it chooses. But if I look around, I don't see any others that are looking like they're out of place. And so I can reorient and set my points back to default. And that looks pretty good to me. So now I will save that. So I only have the cloud that I want selected and checked. And I'm going to say File, Save. It always remembers the last location you were working in. So remember to move it to where you want it to be. And then I'm going to call it I like to call it clean cloud, showing that it has been cleaned up. And save. Original resolution, okay. And it looks like in this cloud there are a little more than 30 million points. Okay, finished with that now. And now we're going to go back to our LiDAR tools software. And instead of create last, we're going to go to create DEM and load in that file that we just cleaned up. And we have our DEM spacing set to 25 centimeters. That's kind of our recommended value. If you have things with high relief, such as a building that you're flying over, then you might benefit from going a little bit higher resolution, like 10 centimeters or so. But for the majority of applications, 25 centimeters is more than sufficient, and you don't gain much by going higher resolution other than larger file sizes and more processing time. So we find 25 centimeters to kind of be that good middle ground, and then we have the option of min, max, mean, IDW, standard deviation, count, or all. And if you hover over, it'll give you a little description of what each means. Typically, we're going to use the mean number, the mean output value. But if you're working with like trees or forestry or something like that, you might consider the max. And you want to make sure you only choose one of these values. You can make a elevation model that has multiple, but that just can't be used for your hyperspectral processing. So for the DEM value, the DEM that you're going to use for your orthorectification, just select one of them. So today we'll do the mean at 25 centimeters, and I'm going to give it a unique name. So 25 cm mean DEM. And we call it a DEM, but it's really a DSM surface model because it includes all of the trees and things like that in it. But for our nomenclature, we call it a DEM. And then we say go. And it is finished. So now if we go into our data directory, we have our point cloud and our elevation model. We have our individual LAS files from the LiDAR processing. We have our RDRF, which means that this cube has been converted to radiance and then reflectance for each cube. And we have our SBET. So at this point, we are done with our processing steps, and we're ready to move on to orthorectification, which we will cover in a subsequent video.